Now let us see the procedure to find A inverse by adjoint method. Now here the A inverse is given by a direct formula as 1 upon determinant of A multiplied by adjoint of A, where the determinant of A is not equal to 0. Now we have already seen the process of how to find the adjoint of any given matrix A. So using this formula we can calculate the inverse of the matrix. So let's see one example in which we have to find the inverse of this matrix by the adjoint method, right? So as a first step, let us first calculate the determinant of A, and we have to make sure that it is not equal to 0. Right? So we write the entries in the determinant form now, and now we expand the determinant along, say, first row. So we have 2 into 3 minus 0. Then the middle term is 0, so that will have the answer as 0. And lastly we have minus 1 into 5 minus 0. So which in turn gives us 2 into 3 is 6 minus 5. So that is equal to 1, which is of course not 0. So therefore A inverse exists. Alright, and to write the formula for A inverse, we know that it is equal to 1 upon determinant of A into the adjoint matrix of A, right? The adjoint of A. Now let us recall the formula for calculating the adjoint. It is nothing but, the adjoint of a matrix is nothing but transpose of the cofactor matrix as per the definition of adjoint. So that means we have to first calculate the cofactors of all the elements, arrange them in matrix form and take its transpose, which is the adjoint. So now if we think about the cofactor, that is denoted by capital Aij, is given by the rule minus I raised to I plus j times the minor of the corresponding element. Right? So the cofactor is nothing but minor multiplied by either plus 1 or minus 1 based on whether I plus j is even or odd. Right? So that means we can calculate all these minors even orally and put them in correct place by attaching either plus sign or minus sign. Right? So therefore we have cofactor matrix of A is equal to, alright, now let us suppose think that we have to write the cofactor of this element 2, right? So skipping that row and column, we have the remaining elements as 1 into 3 minus 1 into 0. Right? Now that value turns out to be 3. Right? So therefore we will write 3 in this particular place, and here the row number is 1, column number is 1, and 1 plus 1 is 2. So therefore the cofactor will be same as the minor. Right? Now let's move ahead and calculate the cofactor of element 0. So skipping its row and column, we have the product of 5 into 3, which is 15, minus 0 into 0, so that is 0. So you see the minor of 0 turns out to be 15. But if you see, this element 0 is in first row and second column. That means 1 plus 2 is an odd number. So therefore whatever product we had got as 15, we must attach the minus sign to it. Alright. Now moving ahead, similarly we complete the cofactors of all the remaining elements. So here we will have 5. Then next would be element 5, and there we'll have the cofactor as minus 1. Then we have 6. Then we have minus 5. Sorry, it will be minus 2. Lastly we have 1, then minus 5 and 2. So therefore this is the cofactor matrix. And now writing the transpose of cofactor matrix, we will get the adjoint. So transpose is nothing but we have to merely interchange rows and columns. So therefore here we will have 3 minus 1 1, then minus 15 6, and minus 5, and lastly 5 minus 2 and 2. So that is the adjoint. And now finally we use the formula, that is A inverse is equal to 1 upon determinant A into adjoint A. But here we have seen that determinant of A is nothing but 1. So therefore finally we get A inverse same as the adjoint. So therefore A inverse is nothing but whatever matrix we have got as adjoint. So that's the way we find the inverse by adjoint method. Now let us move ahead and see some properties of adjoint as well as inverse of a matrix. So these are some general results which can be directly used. So here are those results. First one is product of A into adjoint of A is equal to determinant of A into I, where I is the identity matrix of the same order as the matrix A. Then next is adjoint of product AB is equal to adjoint of B into adjoint of A. So this particular rule is called as the reversal law. That is because if you see, the order of matrices gets reversed on both sides. So on left hand side it was AB, but on the right hand side it becomes BA. Alright, so that is important. That is called as reversal law. Now moving ahead, we have the third property, that is adjoint of A transpose is equal to adjoint of A whole transpose. So that means you can first take the transpose and then take the adjoint, or that is equivalent to taking the adjoint first and then taking its transpose. Right. Moving on, fourth property is determinant of adjoint is equal to determinant of A raised to n minus 1, where n is nothing but the order of the matrix. The next property is the inverse of A transpose is equal to transpose of A inverse. So that means the operations of transpose and inverse can be interchanged as shown here. Next, in the sixth property, we have inverse of AB is equal to B inverse into A inverse. So here also we see the reversal law, that is the order of the matrices gets reversed, similar to the property number 2. Then the seventh property is determinant of A inverse is same as determinant of A raised to minus 1, which is nothing but 1 upon determinant of A. Right? So that's a reciprocal of value of the determinant. Then eighth property is whenever we raise the A inverse to some power k, then that is equivalent to taking the inverse of A raised to k. So here also raising to the power k and taking the inverse, these two operations can be interchanged within themselves. Okay, ninth is an important result, that is it's saying that A inverse is always unique. That means for any given matrix we will always have a unique inverse. That means there cannot be more than one inverses for a given matrix. And lastly we have adjoint of A is equal to determinant of A raised to n minus 2 multiplied by the matrix A.